Good morning. How are you all this morning? There's one person. What about the rest of you? Who's suffering badly? Suffering. You know, life, maths, stats, weather, COVID, anything. Not COVID, I hope. How's the course going so far? Nasreen, you're right in front of me. So am I. So am I. Yeah. What do they do here? What are they doing for you? Mm. All good? Yep. Okay. Anything we can do differently to help support your learning? Oh, good. Yeah, because maybe you haven't done the earlier stats, have you? Didn't do stats 241. That's why it's harder. But as you can see, it's going to get a little more familiar as we go through. So that was just introduction to linear modeling. In my opinion, the whole thing is the wrong way around, because you start with the basic normal based modeling, because that's more natural in some ways. You've got data that's continuous. You just want relationships between two variables that are either continuous or categorical or otherwise, but at least the response is continuous and you've got nice behavior there. When you get to count data, things change a little bit, and you can understand why it changes if you've done the earlier part first. Nonetheless, we'll live with it. So as I was saying earlier, next year it will be a different course altogether if I am teaching it. I'm sure it'll be different if somebody else teaches the thing as well, but we'll see how it works out. Other than that, the first assignment, I think the test has probably mainly been marked by the tutors. It takes a while to mark those things. Of course, I can appreciate that. The effort you put in, it probably take you, I don't know, a few days to do the assignment. It takes them a week or so to mark it. And they're both very thorough markers, so you can, I hope you got, please do look back at the rubric and have a look through that. I am not sure whether I'll put the rubric so you can see it before the actual submission. But I think because there is a marking scheme that goes with the test, it shouldn't be too bad. I'll consider what's going on. Later, as we start, so the thing is, in the end, you never present the work you are presenting in the format you are presenting it to me as an assignment question, a test question with parts and the rest of it. Usually it's going to be, I've got some data, I've analyzed the whole thing, and here is what I've actually found out about it. And mainly you're going to report to non-statisticians. So you've got to, as I keep saying, you've got to make sure that you understand the context and then report the thing back in the context. And often you're working together with people. I'm working with someone at the moment in Subiaco who actually is a knee surgeon. And he has got this new way of doing things, which he thinks is fantastic. And actually it is quite fantastic. But I don't want his services, don't want my knees messed with. So we're working together, but the thing is, he just sends the data to me. And because he's worked with the thing for the last 5 or 10 years, he knows exactly what the data is all about. I don't. I have to ask him, what does this mean? You know, LOS, what does LOS mean? Length of stay in the hospital. He thinks it's natural, it's not natural to me. Yeah, so those things we sort out. But by the time I've got to that, I understand the context and the data and what he's looking for, and I can report it back to him. I'm going to say p-values and those kinds of things, and you know that this is, but I'm going to explain the thing back to him in terms of his context and say, is his knee method better or not? That's his main question. And how does that figure, because it's not just the method, of course, because the data consists of the age of the patient. You look at something who's 30 and somebody who's 90, big difference, yeah, in how the recovery time, all the rest of it. And then you take a look at the overall health as well, BMI, gender, all those kinds of things have to be part of it. And you look at all those. Of course, the main thing is, my main interest, or his main interest, is in this way he's got now of aligning the knee after surgery or during surgery. But we want to make sure we account for all the other differences as well. For example, difference in the genders, difference in the overall health of the person, difference in the age. After accounting for all those other differences, if I can say that yes, this method is better than the other one, that's what we're looking for. Yeah, that's where regression comes in. Now, as we will find out as we go out in the world, many people just don't understand their stats. We had a recent PhD thesis by a student of mine who was working in child health in sub-Saharan Africa, looking at diarrhea and underweight and all those kinds of things. And one of the examiners who was in the medical area didn't understand the stats. So we had, what you usually do is you put all the variables in the model and see what's significant. When you have a large data set like we had, massive, something like 700-800 variables and 10,000 data points or something, this is 7-8 after trimming it down and then trimming it further, you still end up with about 80-90 variables at best. So you find some unusual significances sometimes. So if you just put everything in the model, like looking at income of the person and looking at the gender and the education and the age and all the rest of it, you put in something like eye color or hair color, sometimes it becomes significant. And people sometimes take and blow this up in the media. This is not, it's just spurious. You're getting some significance sometimes that don't exist there. So we had some of those kinds of things in this study as well. But the point is, we can't disregard them yet because we might not understand what's behind it. So our job is to report the thing is, this is what we found. We can't explain these ones here. Somebody else might find later, okay, there are reasons for this. But the examiner's point of view was, well, if these aren't significant, why did you have in the model in the first place? You should look at them pairwise and pick out those that are significant and then put them in the model. That's totally wrong. Because the way multiple regression works is the presence of one variable can affect the significance of another variable. So you can't just put them one by one. You have all those kinds of problems with this kind of modeling that people do all the time and just totally get it wrong and don't understand why we insist on doing things differently. So you'll have the same in your life as a data analyst and data scientist. So watch out for those kind of things. The big problem is trying to resist these things over here. And one of the stories I keep telling all my classes is there was one of our people over here who was a world leader in an area. If I get a chance, I'll pull him over here for a guest lecture if I'm able to. But he's looking at something what's called Stereology, which means essentially if I'm going to try and if I've got a rock from a mining site somewhere and I want to see how much gold there is in, I can send the thing off to Perth from over there, whatever, to have it assayed and analyzed, and it takes me 3 weeks to work out how much gold there is. I'd rather actually do it right there and then because I haven't got one rock, I've got some 50, 60 rocks and I keep moving around the place to find out what's going on. So the point is, can I do it fast and quickly on the site? And this area of stats looks at what's called, what we do is we slice the rock, and by looking at the surface of the rock itself and looking at the area of gold versus the area of the whole lot, we can actually work out how much gold there is. It takes a bit of care as well, as I'll show in a second. But he's the world leader in that area. Now, you take that and change that context to say something like the kidney. You slice through kidneys and you count the number of cells in there. You go to the liver, you go to the brain. Very different things, right? Counting isn't as easy as you might think it is. It's massively difficult to count things properly. So he did this, he worked into this area for a little while with some colleagues. Then he sent off his findings to the medical journals, and they rejected it, saying, what you've done is wrong, this is how you should do it. And he had to argue with them for 3 years, showing why he was right. And eventually they agreed with him. Now, the problem, of course, is that you get people whose careers have been built on what they've done for the last 20 years or so, 30 years or so, right? They're not going to track back so fast. To me, it's a pity because once you realize you're wrong, what do? You change. Fast as that. Because the sooner you change, the more progress you'll make. Yeah? We should be, in my opinion, in this life, be seekers of the truth. When the truth comes to you, you accept it and you move according to that. Eventually, these guys did change, but the thing is, when they did change our understanding of how things like the kidney and the liver and the brain functions. And that's massive, right? That's what we call a quantum leap, all of a sudden, in how these things change. So especially brains, and people always kept thinking that as you get older, the brain starts shrinking and you lose the number of neurons and all the rest of it. What a pile of rubbish that is. Yeah, some say the physical size of the brain may shrink a bit more, but you're still as good at 16 as you are at 60, or 70, or 80, or 90. Yeah? It's a matter of how you look after this one, what you do with it. Now, if you actually always outsource intelligence to this thing, these things get smarter and smarter, and you get dumber and dumber, right? That's the other thing. I've started a memory club here, actually, which has been meeting for the last 2 weeks on Wednesday afternoon. I meant to bring my star student, my recruit, if you like, a lady, a little, well, not quite a lady, I suppose a lady, yes, but a student, a girl who's I've been working with for the last 3 years or so. She came and found me in year 11 in our open day. For some reason, she came through the open day display we had, walked out and came back, and she found and talked to me specifically. I've got no idea why that worked. And she said, I'm struggling with maths because I'm doing in year 11 spec and methods, and I've got no teacher in my school. I'm the only one doing it in my school. So she had an online teacher who she'd emailed a question to and hear back about 2 weeks later. By the time they'd moved on to something else, and she had to keep up to date with it. So she said, is there somebody who can help me here? Now, I'm not being unkind to my colleagues, but if she'd gone to anybody else, they'd say, yeah, well, find a private tutor or something like that. Don't bother, you're too busy. But I said, look, all right, come and see me. So we'll work together. So we work together every Sunday. In year 11, you're 12 hours away, of course, COVID, but we work together online for a few things, not maths, essentially, other things as well. She dropped spec because it was too much in the end anyway. And her father kept saying to her, because she passed nothing in year 11 math-wise. In year 12, she struggled passing anything until about term 2 or so. And the father kept saying, why is he wasting his time with you? You're going to pass, right? You're going to go to university. And my wife even said, why are you wasting your time with her? They said, just give it time. And suddenly, about term 2 or something clicked in her brain. The thing that clicked was she started beginning to believe she could do it. And that's the big thing. Belief, as they say, moves mountains here. And when that changed, she started passing. In the A term, maths was the highest mark. Wonderful. Now she's here doing engineering and neuroscience. So we've been working together in many other things. So I took her to the first year classes in maths. And she stood out there. There's a website called Pi Checker. You can go to it. And she typed out pi to 100 decimal places standing in front of the class, off of memory. Question is, when you see magic like that, there's 3 things you must first of all be sure of. The first is there's some talent, but she's got no more talent than any one of you here has. The second is there is a method. Yeah, something happens behind the background. The third is there's effort. Without those 2 things, method and effort, you can't get anywhere. You might make all the efforts in the wrong way. Without the right method, you get nowhere. But the right method is easy. Now, having got pi to 100 decimal places, you can take it to 500, 1,000, 10,000, just like that, with the method. Takes some time and some effort, but it can be done. Yeah. But more than that, it's not something like learning a poem or whatever else, and you might get struggles of it here and there, but you lose most of it. The method is so good, it will stay with you for longer. It might go through a revision or so every so often, maybe every couple of weeks or something, but it will stay with you for longer. How would it be if you could learn things faster and keep it in your head faster? Amazing, wouldn't it? Well, that's what we're working on in the class over there, every Wednesday afternoon, 4 to 5. If you're willing to come along and join us, you missed the first few sessions, you'll catch up fast, I gather. It's in Weatherburn Lecture Theatre, 4 to 5 every Wednesday afternoon, and you see some of the magic we create there. It's amazing, I can tell you that. If you can make your brain work better and more efficiently and learn faster, it's magic. And I'll just share one thing with you while we are here. This stats is boring. Yeah, that's the easiest stuff. This is the more interesting stuff. We'll have time for that as well. I'm going to give you a string of 10 words, and I want you to remember it if you can. Now writing down, just from your head. The first word, I said how many words? 10 words, that's the first thing, so you can count how many there were. The first word, hydrant, balloon, batteries, barrel, board, diamond, nitrous oxide, oxen, toothpaste, sign. 3. How many do you remember? Shout out.
3 hydrants.
Hydrant?
Yeah. Balloon, barrel.
Okay. It is. Oxen. It is. Struggling. Not bad. So there's two things there that psychologists will tell us about. It's something called primacy and recency. Primacy, the first things usually stick in your head. Recency, the last things you heard, the most recent things you heard stick in your head. The middle part gets lost. These are just 10 words, right? So let's see how this actually works. And I'll explain the idea behind this. So you're walking along the road, and you see a fire hydrant. Now attached to the fire hydrant is a balloon. It goes up in the air, and out of the balloon falls batteries, which are getting caught in a barrel on the ground. And attached to the barrel is a board. On the board rolls down a diamond into this nitrous-charged car. The car is parked between two oxen. And you walk past them, and they've got the worst breath you can think of. You take toothpaste, and you brush the teeth with it. Then you throw the toothpaste into a sign. So the first word, hydrant, yeah. The next word, tied to balloon. Next, batteries, barrel, board, diamond, nitric oxide, oxen, toothpaste, sign. Simple, right? Now let's take this somewhere else. Who here does chemistry? Had heard of chemistry at least, right? There's this thing called the periodic table in chemistry. The first element, hydrogen. Hydrant, hydrogen. Balloon, helium. Batteries, lithium batteries. Barrel, beryllium. Board, boron. Diamond is carbon. Nitrous oxide, nitrogen. Oxen, oxygen. Toothpaste, fluorine. Sign, neon sign. You get the first 10 elements of the periodic table, just like that. Now my class over there, Wednesday afternoon class, first 10, next 8, and the next 8 week by week. Yeah. By the time we get to about week 12 or so this year, we'll have the whole periodic table in our head. You might think, what's the point of it? The point is, this makes your brain work better, more efficient. It's exercise for the brain to memorize things. So you can memorize things very much faster and keep them in here for longer. Yeah? But the thing is, what we've done is we've organized it in a particular way. This idea is called a memory palace. Sometimes people call it a memory map. It's an old idea, centuries old. The ancient civilizations used to use this all the time. You find somewhere, in some civilizations, you've got stones and rocks and things that make no sense to anybody else. But see, these were how they recorded the history, by having these locations and then talking about the locations. The indigenous cave paintings to us look like artwork, not a chance. They are their history. These are their memory maps. That's how they record the history. That is why it's so important for them. To us, it makes no sense. This artwork for us. It's not artwork at all. It's actually how they record the history, by these pointers as memory maps and locations over here. So you can see the idea is very broad, and you can actually learn anything this way very fast and keep it in your head for longer. That's the whole idea behind this. Now, you know, it's interesting how the world changes. My grandfather was born in the place in Fiji, and he lived his entire life there. Didn't go very far anywhere. He traveled, I think, once internationally, only once. My father, where he was born, his entire life there. Fiji is a group of islands. He traveled from one island to the other sometimes. Other than that, that's where he lived, and that's where he, you know, was the end of him. Whereas the world is far more mobile now, yeah, and changes. There's no chance that any of us, very few of us, will stay in the same job for the rest of their lives, or the entire life with one job only. Things change very fast. My son did IT over here. Now he's, of course, my whole family is in Brisbane, so he just changed his jobs this year after 3 years working in a place. That's how it works. If you don't change as young people jobs in 3 or 4 years' time, you get stale in the same job. It's hard then to change afterwards. And of course, changes mean going upwards as well, but also broadening and learning more in different things. Yeah, That's how it works. If you get stuck in a job somewhere, they start mistreating you. Like people, never mind, I won't go there. It's unusual actually. The only place that usually happens is academia, and even now you can see how hard it's getting over here. So the important thing is, the faster you learn, the more you will earn. That's how it works. So if you can learn fast, you've got the edge with everybody else around you. Yeah. Now, one of the things I have developed over time myself is speed reading. It's a magical thing to have, because the most common thing we do in our lives is read. Things come by our desk, you read. Leaders have piles of paper coming through their desk. I don't think they read most of them, which is a pity, because they should. If we sign something, read it, right? Know what's going on there. But more than that, if you can read faster, you can read more. And more than that, you have time for other things as well. So my colleagues and I, when I have to do things like together, like read a paper or something for a student or a PhD thesis, to mark PhD thesis, you're given something like 6 weeks, yeah? Is this sound working? Maybe the speaker isn't on. This is on. So you get 6 weeks to read and mark a thesis, yeah? And invariably, examiners will be late. And so you find, especially with our students here, some guy gets 6 weeks and so 3 examiners. One person is always going to be late. Sometimes they're something like 3 months late. Now, I get a PhD thesis to examine. It takes me 2 afternoons. And now this is not just like reading a novel, you see, it's technical stuff as well. Sometimes maybe 3 if it's really difficult technical stuff. But it's 2 afternoons, one to read the thing, and then one to write my report and submit it is done. We read papers for students. My colleagues, one fellow, not very far from where my office is, I won't mention your names, he's been sitting on this for about 6 weeks. I did the thing in one afternoon and send the thing out to my student. I can do things faster. It's efficient for everybody else, but then I have time to do other things, like the memory club, yeah? That cost me time and effort, preparing myself as well for that kind of stuff. I spend an afternoon a week in Penrose College, or the girls' college, yeah, over there. And I do math stuff and this kind of stuff with him as well. And that takes time as well, yeah? So finding all this time for things means what you need to do to earn a living needs to be done better and faster. Because, you see, in many ways, work is our life, yeah? Because if your work is miserable, your life's miserable. That's why I keep saying to people, saying students especially, I live in this place across the road called Uni Hall, now Curry Hall, before for 27.5 years, mostly, probably more than your agents here. And I have seen students come and go for years and gave them all kinds of advice, including lifestyle stuff and everything else. But the key thing about what I should do, the key thing is follow your passion. What's your passion? Follow your passion. Because if it's something you're passionate about, you'll do it, and you'll do it well. And hey, boy, it'll be fun for you. It's like what I'm doing. This is my passion. I knew I'd be a teacher when I was in something like grade 3 or 4. And the other passion I had was maths and stats. To put them together, magic. Life is magic. Because if your work is miserable, your whole life is miserable. You take it home with you. Your home becomes miserable. Yeah? I've seen this. That's why you get nothing against anybody. You get people who in their 50s come back to university to do something else. Right now they're following their passion. I was lucky because I made the mistake in my life. I didn't follow my passion. I actually did engineering first because that's where maths was used more in than other subjects. And because I got a scholarship for engineering, not for maths. Nobody gives you scholarships for pure sciences. But I was lucky to be able to come back again, right? To be able to do my maths and stats degree as well, which was fantastic. The engineering, by the way, wasn't wasted. It's really very, very useful because my research area, my primary research area actually deals with quite a bit with those kinds of things as well, which is lucky for me. But follow your passion and you'll find your life is good. So work, while is there and is important for us, work isn't our life. The university can kick me out tomorrow and done. Regardless of what I do here, how much passion I have, doesn't make a difference to employees, right, anymore. The age of loyalties and those things are gone by the way. Now it's all about money, unfortunately. Never mind, that's another story altogether. But you see, if you follow your passion and your work is good, most things are good. But this isn't your life. Work isn't your life. There is another life afterwards. If you can do your work fast, efficiently, and get rid of it fast, you have time for living. Because after all, You know, we work for a living, right? We don't live to work. We work for a living. So make sure that your work doesn't become your life. You have a life afterwards as well, or some other stuff. Anyway, so I want to go back to this counting stuff for a second. So we were talking about counting things and how this professor was counting brain cells and all the rest of it. So this brain cell thing idea is, and lucky thing is, people think that brains sort of tend to go away with age, all the rest of it. To some extent, that's true, but it depends how you do what you do with the brain, right? So by and large, one of the things we can do is these kinds of exercises I was saying. But counting things, so one of his examples he kept giving all the time is he's got a bowl of jelly. Here's my bowl of jelly, yeah? And I'm going to put a banana in the jelly. So here's my banana. If I slice the jelly from the top, what I'm going to see over there from the top is these two bananas. But there actually is only one banana in there, not two, yeah? So you can see how important it is to count carefully. And that's a problem that was around with the way the medical people do the thing and the way he does it, properly and carefully. So you can see there's quite a bit of difference in how difficult it is to count things. As far as reading is concerned, this is something that is easy to do. Fast speed reading is easy to do, but it takes practice like anything else. So here's the trick to this. Pick up a book and read. Don't read things online because you can't practice speed reading online. You can practice the thing in hard copy things and translate the thing to online afterwards. So start reading stuff because, again, as I said, practice is what's important here. And I read every night before I go to sleep. So you pick up something like the Da Vinci Code. There's a 700 book page, right? And I read every night before I sleep for about 10 to 15 minutes maximum. And I read a book about that thick in about 3 to 4 weeks, done. And it's easy as well. I enjoy reading very much as well. The way to do is, when you read stuff, the first thing is, when we first started to read, we usually, all of us would read like this. Being babies, we read like this. Was an emeritus professor of, with a finger, right? Or whatever else. By the time we get to grade 2 or 3 or so, a teacher says, come on, Johnny, you're big now. Don't use a finger, just read like that. And Johnny just like that. And that's how Johnny's been reading ever since. The thing is, our eye actually reacts to motion. Yeah? So the finger is a good idea to have. Something that you have there that forces the eye along, if you like, guides the eye along. Otherwise, you're forcing your eye along the line, and that is hard. But with a finger or a pen, this is much faster and much easier. That's the first thing. Use something like that to point out and go along the lines, right? Now, the second thing is, when most of us read, almost all I would suspect, is we sub-vocalize. In other words, there's a voice reading with this in our head saying those words to us, right? So if I read a thing in my head, I'm sub-vocalizing the whole thing. Now, most people speak about 250 to 300 words a minute. I speak a bit faster, I know. Yep, I'm trying to slow down. But that means our brain is much, much faster than that. And if you don't give the brain enough information, it starts wandering somewhere else. And that's why I can read the whole page and say, what did I just read? What was it? You have got no idea what you just read. Because your brain requires information at a faster rate than you're giving it, so it goes somewhere else. So people say, when you read some stuff and don't get it, they say, I'll read it again more slowly, and that's the worst thing you can do. Speed reading gives you higher focus, like driving at 10 kilometers an hour versus 250. 250, you're already focused. 10, you can just look around, play or whatever else, on a mobile phone. But when you go faster, you require more focus. So speed reading focuses the brain better. And you actually understand more as well. So the trick is, use your finger, but try and stop sub-vocalizing. Because otherwise, your reading speed is limited by a talking speed, which is much lower than how fast your brain actually works. The brain is an amazing piece of equipment, absolutely massively amazing. More than that, you see, not only can we make our brain more efficient, we can actually grow more neurons by exercising it, like these kinds of things. You can actually grow your brain. That's amazing. So this requires practice, though. The first time you try it, for the first 2 weeks, 3 weeks or so, you will actually slow down. And that's fine. Like anything new you try, you'll be doing it slowly, you start of it. But after 3 months or so, you suddenly get this ramping in speed going up. Yeah. Now, if you can practice that, just sit down every day before you sleep and read something, pick up a book and read it. Yeah. You'll find all of a sudden your reading speed goes up the wall. Now, students complain to me sometimes saying, I've got so much reading to do. Hey, don't just speed read. Don't just speed read. Spend some time, invest some time in this, and you'll find how easy your life becomes. Yeah? Because you don't have to worry about, I have to read this stuff, oh my goodness. Hey, bang, just like that. You can read a book a day just about, if you find the right kind of incentive, because essentially all learning is based on the state of your mind. It's all learning is state-based, right? So if you have reason to do things, you'll do it properly. I keep saying this thing, I'm not sure whether I asked this class this question. I did ask you the question of why you're here in the first place. The why is important, because the why focuses you and the why drives you, yeah? That's the whole thing here. So there's a story I keep hearing from one of my people I look at sometimes and work and see what he or she is doing, is that saying that this one of the people who he works with read a book a day, but there's a reason for that. See, her mother had cancer, and all the doctors had given up. So she wanted to learn about the disease. She read a book a day and gave her mother advice. And guess what? Her mother recovered. There's a focus behind it, right? So if you have reason to read, you'll read. But in the first place, just practice the speed reading, and you will find how fast things become for you and how your life changes. Amazing. So try that first. Anyway, back to the maths and stats, the more boring stuff, the more sort of routine stuff. So last 4 weeks or so, we've just played around with some data. We've begun to start looking at binomial stuff last week or so. And you'll find some of the binomial kind of tests in the R notes I gave you earlier. So you'll find there we're looking at testing for one proportion and for two proportions there as well here. But here we'll start looking at count data and looking at count data in the form of tables. So tables of count data is our interest today. And the usual story is, if you've done the first year stats, then one thing we do is what's called a chi-squared test for goodness of fit or for homogeneity or independence. And there's a bit of sampling schemes that I've left in the title here, but I've taken out of the lecture notes. It's not so interesting, I think, for this class, and probably a bit more than we should actually be doing. So I've taken that out for the moment. And there's other thing called Fisher's exact test that relates to also this same kind of test. So you'll find all the material we're covering here will be in this week's lab. And the test, of course, is based on last week's lab. So you have done that, you get the solutions. I expect it'll be much easier this time than the last one. So count data, essentially, what we're looking at essentially is grouped data. So you've got two categories, essentially this way, category 1 and category 2. And they've got labels, say L1, L2, whatever else, and the same here. So the things we're looking for essentially basically are going to be to do with distribution of things. In other words, is the distribution homogeneous? Is it the same at all levels of one variable? And the other thing is independence. And they both actually have similar ideas. In fact, they work exactly the same here. But what we've got here in the cells is we've got counts of things. So each of the entry here corresponds to the count for each of those levels of the categories here. And the idea, usually call this thing as a contingency table, a two-way contingency table. The ideas we see here, as we saw with things like, say, the seatbelt data, there was a table essentially of the similar kind, and the battery data with temperature and material was similar kind of materials, similar kind of tables we saw here. We've got two categorical variables as a two-way table here, and one variable can be thought of a response. You usually with fewer levels, 2 or so, maybe 3 if you're unlucky sometimes. And we want to see what's happening with the counts in this variable, but with respect to the other variable here. So as far as homogeneity is concerned, we're looking to see if the proportions of the response variable is the same for all levels of the other variable. The example here is the Titanic here. We've got two categories here, the type of the passenger and the survival, which is alive or dead here. And we're going to see here whether the status, survival status, is the same for all types of these passengers. In other words, is the proportion of survival of those who survive the same for the crews and first, second, third class passenger. That's the interest here at the moment. All the commands are given here for R, and you'll find this data frame is one of those that's built into R, so not very hard. You'll find some of them later on, but here we actually read the data in by hand, created the levels that we saw. So we've got the GL, the generate levels for both the status and the class. And here are the bar plots here. So this is the bar plots of just the counts of the data, essentially frequency for each of those particular levels of the type of passenger. And we've got here survived or not survived, alive or dead. And by looking at the numbers only, you might find that maybe it looks like the crew, more of the crew died. But we can do better than that, so we can try and take a look at the data as proportions. So here, all we've done here is dividing each number in the table by the grand total. So the grand total was here, so that divided by itself is 1. Everything else is proportion. So essentially 32% of the passengers survived, 68% died, but in each category, if you look at it, you'll find that 10% of the crew survived, 31% died 10% of the passengers, 10%, it's not quite right to say 10%, but 10% that died 10% that survived were actually crew members, 31% that died were actually crew members. The more important thing to do is to look at it in another way, which is proportion of each type of passenger that survived or died. And you can see here it's more clear now that 76% of the crew died. Yeah, of the ones that survived, of the first class, 62%, of the second class, 41%, of the third, 25%. So it doesn't look like there's a uniformity there or homogeneity there. Certainly expect more of the crew not to survive because the crew will be busy trying to save everybody else there. But as far as the other passengers are concerned, it looks like the first class, most of them survived, or more of them survived, and the second, the third. And that's what we're looking at here. Is this actually what we're seeing here? Are the differences here significant? And we can do that by these tests. So all the R commands are said here. All we're doing is dividing here, making tables, and then make the division here as proportions as we want. So what we're looking for here, essentially, if I'm looking in terms of probability for those interested, I'm looking at probability of here dead, given that the passenger was a crew member. And the same here, probability of survival or death, given the passenger was a first class passenger, second, and so on. So I've got essentially I've normalized each column here by the column total, and I've got the percentage of survival for each of those. And now if you look at the proportions here, it seems much clearer as to what's going on here. We've got alive and dead. You can see that in each, except for the crew, of course, because they're a special class altogether, the alive and dead seems to go with the class of passenger. The first class more survived, higher proportion survived here versus the other one. By the time we get to the third class, most of them actually didn't make it. So what we're going to do over here is, and I was saying conditional probabilities, that's what we got there. So the probabilities are conditional here. What we're going to do here is take a look to see if the proportion or probability of surviving essentially is the same for all classes. So that's what we're looking at here. Same distribution across the different groups. Same probability of survival for each of the groups is what we're after. The test statistic here is what's called a chi-squared test statistic. And what that is all about is how we calculate that is. We take a look at the observed frequency that we've got, and that's in the table as it is. And then we can work out what's an expected frequency under the hypothesis, which is the observed data has the same distribution. So assuming the distribution is the same, I can actually calculate what I call the expected frequencies. So the difference squared upon the expected frequency is what we're looking at here. Now, we'll understand this more clearly later as to why this works that way, and what this chi-squared distribution is all about. We'll explain this afterwards when we've done a bit more work later. But this is the idea here. And so these calculations are easy to find, to do here. For the chi-squared test, it's always a one-sided test here. And because it's a square, it's always positive as well. So we're looking always to see whether it's big or not so big. So the p-value always will be looking at things like what we have seen here, probability of the chi-squared distribution with some degrees of freedom here being bigger than what we observed here. So the chi-square distribution, Barneville comes with two things, n and p. Normal comes with mean and variance, and the chi-squared comes with degrees of freedom, which we have to calculate. And the degrees of freedom are worked out by number of rows minus 1 times number of columns minus 1. Or if you like, number of categories in the first variable minus 1, number of categories in the second variable minus 1. In other words, you take a look at whatever's on the top and bottom, number of rows or columns, decrease by 1 and multiply, you get the degrees of freedom very, very easily. So in this case, for the chi-square distribution, what we had here was we've got 2 rows and we've got 1, 2, 3, 4 columns. So the degrees of freedom here would be the number of rows minus 1 times the number of columns minus 1. So that comes to 1 times 3, which is 3. Easy to work out. What does the chi-square distribution look like? Well, I'm going to plot some of these here for you, and all the R code is here. You can try and do this thing yourself. But here are the plots here. So the first one is for chi-squared 5 degrees of freedom. Then we get to 10, and then we get to 15, and we get to 20. You can see as the degrees of freedom increases, the first one, 5, is actually skewed to the right. Yeah, it sort of goes up, and then there's a tail that goes to the right. They all have a bit of a tail. By the time we get to 20, the tail actually almost smooths out. So it becomes more and more normal. As degrees of freedom increase, this approaches the normal distribution. So for large degrees of freedom, chi-squared becomes normal. Now that's not important for us, but it's just by the by. And generally speaking, with this kind of data that we're looking at here, you don't get degrees of freedom very large. Usually it's 3, 4, 5 or so. You don't get much higher than that usually. So in other words, you are looking at a skewed distribution. And while we're with this kind of thing over here as a plot, the p-value will lie in the tail. So the p-value usually will be this probability over here somewhere. When I'm looking at the chi-squared, it's going to be something, my observed value will be somewhere here, and I'm looking at something bigger than that. So it's always going to be, in this case, you don't think in this case as a one-sided or two-sided test. It's always one-sided in one sense because you're looking at everything bigger. But the p-value here, in that case, will be in the tail, always the right tail. All right, assumptions here. Well, we're going to have some assumptions. The first is that the data actually is counts. And we've got in each cell the count for the particular values of the categories, levels of categories here. We assume the counts are independent. So we assume that the number of people who survive for the crew are independent of those that survive in their first class or second class passengers. We are assuming, of course, this is a random sample of some kind here. I'm not going to go into details of sampling over here. And the last is a very important one. We are assuming that all the expected frequencies, we said there's a way of calculating these expected frequencies. We're assuming the expected frequencies are at least 5, bigger than 5. If it's not the case, then the thing is this chi-squared distribution here is an approximation, and if the expected counts aren't at least 5, the approximation isn't a very good one. So for the Titanic stuff, then H naught always will say the distribution here, in this case I'm looking for homogeneity. We're saying the distribution of survivors was the same across all crew and passenger groups, and H1 says it's not the same, or simply often people just write H naught is false, and that also is acceptable. Sometimes the alternative hypothesis is more difficult to write. If you've done STAT2401, you'll find in the ANOVA situation, the null hypothesis for ANOVA is that the means is the same for all the categories of values, and H1 will not say the means, it will not say that the means are different. It will say the means aren't all the same, or it will say at least one mean is different, or simply that H naught is false. So either of those is going to be good enough here. And so what we need to do here is we'll test for the conditions over here. Now these are counts, no problems with that. Independence is not something you can often test for. So here essentially it's an assumption that we think there's no reason to doubt it. No reason to doubt this is not random, and the expected cell frequencies is what we're going to be able to work out now. So let's see how this works. The way the expected cell frequencies work is that there are various ways of doing this thing, and I'll let you look at the slides in detail here. I can work out the probability of being alive for each of those particular cells over there. So says the row marginal probabilities are, probability of surviving or alive is just 711 over the 2201. And of course, this is the remaining 1 minus that, or the 1490 over the total. So these are probability of being alive in the rows, and I can work out the same for the columns if I want here. So probability of crew surviving is 885 upon that, and so on and so forth. I can find those probabilities easily enough by dividing by the grand total. And what we need to do here is the expected value is the probabilities times the number overall here. Now, in the end, it becomes simple because you can see what's going on here. This is the row total, and well, actually, this is the column total, I think, and this is the row total, and this is the grand total. So once I cross these off here, essentially this means for each cell, the expected count is the row total, the row sum, times the column sum, divided by the grand total, or overall total. So this is the calculations that we'll do. Now, of course, you can do it by hand, or you can use the machine, and we'll do it both ways. So here's the by hand calculation, and you can see here I'm looking at here the expected counts for each of those particular cells. 4 by 2 will give me 8 altogether, and I'm making sure I'm checking to see if each of them is bigger than 5, and you'll find that every one of those is bigger than 5. So my assumption about that the expected cell counts are bigger than 5 is also met here, no problems here. And the calculations look like this. I've got observed counts in each of those cells, and the expected counts I've just calculated. So observed minus expected squared is what I'm after here. Of course, it doesn't matter how I subtract these because I'm squaring them, but the important thing is I divide by the expected counts. If I do all that, I've got all those counts over there, the sums, the squares over there. So observed minus expected squared of expected, and I'll sum them all. And my sum here will be what my chi-squared observed value is, 190.4011. Now, one thing about the chi-squared distribution here, as I was saying earlier, the degrees of freedom is 3. Now, for the chi-squared distribution, the mean is equal to its degrees of squared. So chi-squared distribution has parameter as degrees of freedom. Mean equals degrees of freedom. And now we know that the further you move from the mean, the less the probability will be in the tails. Yeah? So in this case, the mean is 3, and my observed value is 190 something. So I expect a very small p-value. In fact, it is quite small, very, very tiny indeed. I'll usually give this as 0 essentially by the time we get to it. There you are. It's 0 times e to the 0, 10 to the 0. So it's quite tiny, very small indeed. So in that case, certainly we have sufficient, a very strong or conclusive evidence against H0 here. So we're going to say here that there certainly is no homogeneity. In other words, the probability of survival isn't the same for all kinds of passengers of crew. And by looking at those particular calculations for the chi-squared distribution, and we'll see something later on as well, but looking at, if you look at the counts over here, you can very easily find where most of the discrepancy lies. See, the ones that have the most contribution to the chi-squared value are where the problems lie. That's the first one, that's the biggest one, and that's the first class alive. Now, if you look at the numbers here, the observed was 203, right? We expect, with the observed, 203 of them survived, but I'm expecting only 100 or so to survive. So, in other words, many more here survived than expected. That's where the discrepancy is. In the first class, many more survived. Now, if you take a look further down to, say, the third class, see what's going on here. The observed that survived were 178, but I was expecting many more to survive. So very few of the third class survived, and I was expecting more to survive. The death the other way around, you can find, is not so difficult. Yes, 528 died, whereas I should have 477 died. So more died than I was expecting. So you can see what the differences here are. There certainly is here a bias, if you like, in survival towards the first class passengers. The crew, of course, you can see is the next largest in the contribution. In fact, no, sorry, the first dead is the next largest, where you've got far fewer dying than expected. So those two, the first class ones, are the major issue over here. You go Tatting, go first class, yeah? Don't go cruise or third class or whatever. That's the story behind it. So certainly was some bias towards who survived. You can see, of course, you pay more, you're going to get better facilities. So anyway, that's how this thing works here. So the other idea here is if you have done any normal regression, you will find this idea of residual, because as we saw earlier, residual is the thing that tells you how good the model is, in other words, what's left from there. So this is an idea of residual here as well, which we'll see later on. So when I do this in R properly, not this week, I'll leave some examples next week for this, because you can do this R fast. And R, like any other linear object, when it does a test of some kind, it saves certain things from there for you, which you can then examine and peruse and work out how good your model is. So this is easy enough in one sense. I've concluded what was going on here, and by looking at those expected and observed counts, I can work out exactly where the difference and the discrepancy is. And so this is what all this is going on here, is looking at those kinds of counts and things, and I've done that just by looking at those counts straight away. And as I was saying earlier, degrees of freedom here is number of rows minus 1 times number of columns. The next one is chi-squared test for independence. Exactly the same idea, exactly the same thing. All that's happening is the hypothesis changes as to what I'm looking for, right? But the calculations are exactly the same. In fact, I could easily have looked at the Titanic example as independence, saying that the survival is independence of the level of passenger, type of passenger. If it's independent, that would mean it's all the same thing, right? Exactly the same thing in principle. So I make no distinction between those things as homogeneous distribution or independence. To me, they're exactly the same thing. If it's independent of the class of passenger you've got, that means they must all be the same. But here, I'm looking here at, again, two variables. So I've got here hepatitis C or no hepatitis C, and I've got this idea where it comes from, where the tattoo actually was taken. We're going to see whether the risk of hepatitis is linked, related, dependent on where the tattoo was actually done. Nothing changes. Everything's exactly the same. Same test statistic, same chi-square distribution, same way of calculating the degrees of freedom, same p-value, still number of rows minus 1 times number of columns minus 1. P-value is working exactly the same thing. Nothing changes here. And so hypothesis here, the same thing. H naught says there's no difference in other words, the whether you get hepatitis C or not is independent of where the tattoo was made, and H1 says not independent. Or again, simply you can say that H naught is false. Either thing works for me. Calculations in the same way, the assumptions are the same. Of course, in this case, I've got these two groups, and I've got counts over here. Independence assumptions, well, this is all we're saying is that the counts in each of those categories are independent, but that's I'm testing for that anyway. That's not a problem. Randomization, I'm assuming all those was done properly, and the expected cell frequency count is the most crucial one here. I look at this, and I've got my categories over there. Probabilities over here, again, simple thing is going to be the expected counts in each cell. In each cell here, the expected count is going to be the row sum times the column sum divided by the grand total. So here, my expected frequency would be 52 times 47 over 626. And likewise for every cell, pick this cell here, that's my row sum, that's my column sum, multiply, divide by the grand total, you get your you get the expected frequency. So I can work it out that way, or by probabilities, either way it works here. But by looking at the numbers over here, it looks like just proportions across the rows here. It looks like the probability of if you look at hepatitis C itself, looks like the largest probability actually is in the parlor that we get this. But if I do this as a test of hypothesis, as you can see here, all that's happening is the row total times column total, and as I cancel one of these, if I get divided by the grand total, I can work out this by hand. The important thing for me here is I've got this cell here and this cell here where the expected counts are less than 5, and that's a problem because, as I was saying earlier, the chi-square distribution here is an approximation only, and the approximation is good as long as this particular condition that the expected counts are bigger than 5 holds. We'll explain this to you later as to why that's the case here. So the calculations are the same as before, nothing changes, but here my chi-squared is also 57, no problems with that. Again, as I was saying earlier, the mean for the chi-squared distribution is degrees of freedom. In this case, my degrees of freedom is simply just 2. People say degrees of freedom are, but it's 1. Degrees of freedom is how I think of it. It's one single thing. Anyway, that's 2, so the mean is 2, and my value here is 57 something. The p-value is quite small. Again, there's overwhelming or conclusive evidence against H0. In other words, the chance of getting hepatitis C is not independent of where you got the tattoo. And so I conclude here that certainly there is a problem here. Now, as far as working out where the greatest discrepancy is in the chi-squared calculations, I go back to that, and I can simply look at it. Where was the greatest contribution? There it is. I'll go back to the numbers. I'm expecting only 3. I've actually got 17 cases of Hep C. So it looks like the parlor is where you get more Hep C as opposed to the other places. That's the biggest contribution. If I take 43 off there, I'm down to about 7 to 10. The other one is here, of course. If you look at this again, the parlor idea, I'm expecting to have 22 with no, sorry, I'm expecting to have 38 with no Hep C. I've got 22 only. So I'm going to get far fewer without Hep C with no tattoo as opposed to those who have tattoos. So this is how we interpret the thing by looking at it. Once I decide to reject H0, I can work out exactly where the problems are by looking at this. The other idea, as I was saying earlier here, was this idea of residuals, and I'll get to that later on, probably about next week or so. So all those things are there, calculations, and I've done the hypothesis test. I've got the conclusions there as well. Hep C is higher in those who have a tattoo than in the parlor in particular. So these are exactly the same in principle, exactly the same kind of idea. The problem though with this one here, one of the things we need to note here is that the expected cell frequencies are not bigger than 5 for every cell. And that means that my results here, the p-value in particular, because it comes from an approximate distribution, mightn't be that reliable. However, because the p-value is so tiny here, I'm happy to accept that. Nonetheless, you will find in situations where this can be crucial, and you will have, if the p-value is something like, I'm comparing with 0.05 here, if my p-value is 0.03 or something like that, I tend to doubt what I'm seeing here in a very different scenario in that case. So those two are exactly the same in principle, and nothing much changes here. It's exactly the same. However, in situations where the expected counts aren't 5 or more, then we can do something that's called Fisher's exact test. Now, in fact, in many ways, this is a misnomer because there's nothing exact about this in any way at all. All Fisher's exact test does is it actually permutes the observations between the different categories and looks at the probability of getting this particular set of observations that I've actually got compared to all the possible observations that I've actually got. So it's not exact in any sense at all, it's just a permutation test in that sense. So it still is more acceptable than the chi-squared when you've got counts, expected counts which are less than 5 and a p-value that may be a bit marginal. So the way it works is, and the illustration is here, but as far as we're concerned, we can just hit the button and get the thing. As far as what it does is concerned is that, the example given here is that if I'm taking a look at, say, each of 7 men randomly assigned to one of 2 groups. There are 4 men in the first group and 3 in the other group. And each man here decides to promote an applicant based on a personnel file. Group 1 is told that the applicant is male. Group 2 is told is female. Suppose that only A, B, C in the first group and E in the next group decide to promote the applicant. The proportion of the panel supporting the promotion in is 3/4 here and 1/3 there. And so overall though, if you look at the difference here, that's where we get 0.417. And so I'm looking at hypothesis tests essentially here of the same kind, looking at the proportions. I'm trying to work out whether there is a difference here. So the one way to actually test this is if we kept the promotion status the same for each of those in the panel, but I then moved the panel around. So I've still got 4 in the first group and 3 in the second group, but I permute them. If I do that, then the proportion in each group that actually promotes this individual will change. Yeah? For example, I can get all the 4 in one group as opposed to some of them in one and some in the other. So that's all that's happening here. And here's a little table. This is from the book itself, the Stat Sleuth. And so you can see here the original allocations here. And as I permute those people across from one to the other ones, then the proportions change from each of those, and the difference also changes. And all I do here is, as far as I'm concerned, for a p-value, I look at the difference I have, and I find where it is in the rank of all the differences. I've got all the differences here. I find where mine is, and I can find a p-value by saying bigger than that very easily. What's available there? This idea is not very different from what you might find if you do more stats. It's something called bootstrapping as well. It's similar in that sense to that, where you don't actually have a distribution to look at. Sometimes the statistic is so weird, you don't have a distribution to look at, you can't find a p-value from a distribution, so you do what's called bootstrapping, essentially by resampling from the data itself. So this idea here is similar to that, but by looking at this, and I won't go in details here because for us we just press a button to get the thing, but the idea here is this: by looking at this and looking at where my observation is, and working out how different it is from the other ones. So if I rank them over here, you can see probably being bigger than that is going to be, well, count the number of these over here, divide by the total number, I've got my p-value here. So in this case then, my p-value is one-sided, looking at the difference here is bigger than 0 or not. So my observed value here is 0.417. 13 groupings out of 35 produce a difference as great or greater than 0.4175. For my p-value here is at 13 out of 35, 0.37. That's how simple this stuff is. Nothing more than that. In principle, it's quite simple. Of course, doing by hand is crazy, especially if you've got large numbers. Permutations aren't simple to work out. But if you use the buttons on R, you'll be able to get them very fast here. So I won't go here into all the details. Essentially, the p-value comes my way very easily here. But as far as the distributions are concerned here, there's something called the hypergeometric distribution, which we probably haven't seen ever before. But all it is essentially is a matter of selecting things from groups of things, and so it works out to be like that. The details here aren't important for us. The important thing is for us is we can get this from R very easily, and randomization by hand is difficult. Even by computers is difficult. You just want some answers here. So here is another example of the Fisher's exact test in this particular scenario with data as tables, promoted yes, no, male, female, and you can see what's going on there. I can again do this kind of permutation test, but if we just use the commands in R here, here's my data as a matrix, and I've got here the row names as male, female, and the column names as promoted and promoted. So I've essentially got my data here in a tabular form or a matrix form here with the correct names for the rows and columns. If I do the Fisher's exact test here, alternative is greater, difference is 0 versus greater than 0. I find here very easily, it gives me a p-value. It also gives me some other calculations, including a confidence interval. You're aware that what R does is, for one-sided tests, the p-value will be some value, whatever the value is, to infinity. Or if it's a left lower-sided test, lower tail test, it will be negative infinity to some value here. If you want a symmetric confidence interval, you can always work it out separately using R, but here this is how it works. So the p-value here is 0.02, and in this case then I will reject my H naught, which says there is no difference in promotion culture there as opposed to there is. Here's my 95% confidence interval, and you can see what's happened here is now it's two-sided, so it gives me a symmetric confidence interval as much as possible, at least a two-sided interval here. So here my p-value is 0.05 for a two-sided test, right? Now remember what we said here. In fact, my apologies, I didn't say that. Actually, no, this is fine. So my significance level here for a one-sided test should be 0.025, yeah? This is marginal, it's only just less than 0.02. I suspect it's actually printed less decimal places than it should. It's more like 0.02 something. By the time I get to the two-sided test, you can see actually it is 0.05 here, the p-value here. So in this case, I certainly wouldn't reject my H0. You can also see here that the odds ratio, my interval here does contain 1. It actually contains 1, spans 1. So in other words, there's no difference here in the promotion culture for males and females in this example. So Fisher's exact test works that way. The main thing is to make sure you're looking at the right kind of difference for the proportions over here. Otherwise, all you need to do is essentially hit R with Fisher's exact test. Just to go back again, I am using Fisher test over here. I'm going to give it the data frame, in this case is a matrix, and I need to provide the alternative as being two-sided or one-sided. So it's always going to be looking at an odds ratio here of being equal to 1 versus bigger than 1, or bigger than or not equal to 1. So that's that part of it. There are other tests over here, Cochrane mental Hensel test. You'll find people do these kinds of things all the time. Now, all of these things, by and large, aren't as good as what we can do with this. So this is looking at the Titanic example. The Titanic is actually is a very complex data set. So what we've got here is 2 levels for sex and survived. We didn't look at sex before, but 4 levels for the class of passenger. There's 3. We've essentially got something that's in 3 dimensions, right? You've got a 2-way table with a 3rd dimension as well. And we can pick the dimension as we go. If I look at the data here, as the structure of the data, we can see what's going on here. I've got the attributes of this. There's a class of the passenger here. There's the sex of the passenger, plus the age of the passenger is child or adult, and I've got this other status here, survived, not survived. Altogether, there's 1, 2, 3, 4 dimensions here. And so it's the ones we might want to pick. So you can see also this class has 4 levels, 1 to 4. Sex has 2, age has 2, adult, child, and survived is 2, 1 or 2, which is no or yes. So what we're doing over here is, in this one, we're picking 2, 4, and 1, the dimension 2, 4, and 1. So 2 here would be sex. 4 is survived, and 1 is class. Those are the 3 variables we're looking at in this data structure. Survived, class, and so it's going to be looking at the classes first, in survived versus the sex. So class, the first thing is 2, 4, 1 here. The class here is 1. So it's the last thing, if you like. That is the last thing. By class, first class, I'm looking at survival here with respect to sex, second class, and so on and so forth. These are my tables that I've got here. Now, if I take a look at this Cochrane mental Hensel test, taking a look again at Fisher's exact test for count data. This is again still Fisher's exact test here, but what I've got is more than 2 dimensions of the data in this case. The same kind of idea here holds. I'm trying to see whether the odds ratios are equal to 1. So I'm looking at here the class of the passenger in each class here to work out what is the odds ratio of survival for the males and females. Yeah, so class 1, second class. So the odds ratio here for the first class here to start off with. So you can see here my data here is Titanic, I'm looking at first class, Titanic looking at second class. So in the first class, I'm looking to see the difference between males and females for survival, and I've got here the odds ratio. 95% confidence interval is quite large here, and the odds ratio itself is 66, versus here for the second one, I'm looking at the second class, odds ratio is 43, and so on and so forth, third class, and so on. So it doesn't look like we have the same odds ratio through all the different classes. So how do we work out here what's going on here? We can look at a pooled estimate, that's fine, to work out what we can compare for each class with. So we look at each of the classes to work out how it's different from the pooled overall. We can do that kind of difference in the ratios here. But we also need to think about how many individuals in class. So we can't just take the average of those ratios here, because of course there are different numbers in each of the classes. So that doesn't quite work here. So if I just do an overall test for the whole lot. Now in this case the same idea works as before. The chi-squared degrees of freedom in this case is 1. It will be the same idea as before we had. Just going to be the number of columns, rows, and whatever else time 1 less than times that. But the main thing for here that we're looking for here is a p-value to look at to test our hypotheses, and the other thing is a confidence interval for the odds ratio. And the odds ratio here is actually much bigger than the one you can see quite clearly. The common odds ratio, you correctly see, the common odds ratio is based on the whole data and works out, look at the survival versus not survival overall. So the overall common odds ratio does lie in the 95% confidence interval here, but certainly the odds ratio is not going to be equal to 1. This of course is not in the middle, because the confidence intervals for odds ratios just isn't symmetric, unfortunately. You know that we had a look at last week. We're looking at not odds ratio as such. We start off by looking at log of the odds ratio. So even the log of the odds ratio is symmetric. If I go, say, from 2 to 4, by the time I go back to the actual odds ratio, then of course I take the exponential of that. This is e squared, and this is e to the 4. That is no longer going to be symmetric. So that you'll find often the confidence intervals for the odds ratio won't be symmetric. I think you'll find it in this week's lab as well. There is some idea working out how I can take a look to see whether where the discrepancies are, and we saw that earlier by looking at the difference, essentially comparing the expected counts to the actual counts. That's what we did before. The same kind of thing happens here. The expected again is going to be row total times column total divided by grand total, and this is in each class. And the excess is the observed minus expected. This is not too different from the idea of residual, but as I said earlier, R gives you residuals for these kinds of things, which we can actually take a look to see what's going on. The same idea happens as before. You're looking at large residuals, and whether it's negative or positive. Residuals always depend on the idea of observed minus expected. So if it's negative, that means the observed was smaller than expected. If it's positive, that means that the observed was larger than expected. So I don't want to spend too much time on this, because I'm not a very big fan of this kind of test myself, because we can do far better. The last example here, that's from the book as well, looks at the death penalty in the US by race here, and this is a textbook example there. So you can see what's going on here. This is the aggravation level of the crime versus the race of the person versus the death penalty, and this data is in the book. You can pick it up. But here the idea is the proportion of death penalties here the same for the crimes versus the race here. So the relative odds here, death of the white victim murderers relative to the odds of death penalty for black victim murderers is what we're looking for. And you expect this to be the same if there is no bias here. We're testing to see whether there is a common odds ratio of 1 versus not. This is a calculation by hand of the expected, the excess, and the variance. And the excess is what's interesting here. You always compare the expected count with the actual count as well, but the expected was what's interesting. The excess here is larger for those two particular ones. So it says aggravation level and the race of the victim. And we're looking at here the difference between the observed. So the z-stats here comes out to be 3.335. You know that will leave you with a low p-value here because it's quite large. And so here, with this example, the p-value is quite small. So we reject the null hypothesis that the common odds ratio is equal to 1. In other words, the odds ratio, the odds of death penalty for a white victim and the black versus black victim isn't the same. So there's evidence here that the odds of a black murderer being given the death penalty if the victim was white are greater than the odds of the other way around, if the victim was black and the perpetrator was white. So I'll invite you to look at the details in the book as well and go through this carefully, and when you do the lab for this week, you'll find that similar things are being done there. Now, going back a little bit to the chi-squared idea, why we said chi-squared actually is an approximation. The way the chi-squared test statistic is worked out is it was the sum of the observed minus expected squared over expected. The chi-squared itself is actually the sum of the square of normal random variables. So if I've got the standard normal variables, so I've got, say, Z1 and Z2 up till Zn, I've got n of them, and each of them is normal with mean 0, variance 1, standard normal distribution. If I add the squares of those, square them first and add them up, what I end up with is a chi-squared n distribution. Now, the way this works here, why this becomes chi-squared is, we did say earlier that I have count data. Now, the way you model count data is by saying it is a Poisson distribution. So I'm assuming my count is a Poisson distribution. So the Poisson distribution has this thing called the mean, sometimes called mu, sometimes called lambda. And the Poisson distribution, the mean is equal to mu, and the variance is also equal to mu. The variance is also equal to mu. The Poisson is the only distribution that the same mean and the variance, they're the same. The mean and variance are equal. And this is useful sometime, we'll see later on. So my expected value here is my Poisson mean. And this here is also the expected value. It's my variance actually. So all I've done here is I've got observed minus expected upon the expected square root of, and then square the whole thing. So if I've got observed minus expected squared over the mean or variance over this of this. In other words, each of these things actually is a normal not one random variable. So I'm thinking of this, each of these has a normal not one distribution. I'm squaring them and adding them up, and I get a chi-squared distribution out of that because, as I was saying earlier, the idea is these are normal, approximately normal at least. Now the approximation here, in other words, I've got a Poisson distribution which I'm approximating by the normal distribution, and that works well if the mean of the Poisson is at least 5, and that's where the 5 comes in from. So the expected counts essentially are my estimates of the mean of the Poisson distribution, and there must be at least 5 for the normal approximation to be good. That's how this whole thing ties up properly. If you do more of the probability distribution stuff, if you do any higher stats, you'll find how this works. But that's the basic idea here. However, all we've done so far here in the tests so far, for example, even with the Titanic example, we had 4 things to look at: the class of passenger, whether it was a child or adult, sex of the passenger, plus the class, plus survival. 4 things to do. Survival was my response variable. I really want to know how survival depends on all I can say so far is independence or not independent of, say, gender and the type of passenger and whether it's adult or child. All I can say is independent or not independent. I want to quantify that a bit further. And to quantify that, what I need to do is do some different analysis. And that's the kind of stuff we'll start hitting next week when we start looking at some real analysis. The idea behind all these things is they give us ideas of the behavior, odds ratio, whatever else, but it doesn't give us details of how things change for different kinds of the passenger, for example, in the Titanic example. I can't relate this to the different variables in my model, if you like, or in my data, to see exactly how survival depends on each of these separately. All I've got ideas is an overall odds ratio somewhere. Whereas I really want to know the odds ratio for example, a female first-class passenger versus the odd ratio for a male first-class passenger, or a female first-class passenger versus a male second-class passenger. I can't do that so easily with this kind of analysis. That's where we're headed. So next week we'll start looking at those kinds of things, and that's when things start becoming interesting. This is week 5. We hit week 6 next week before the break comes across. Now, because I wanted the tests to be balanced, there's a test this week and there's another next week. So, but the thing is, you are taking 10% for each test, which is great. So you have less things to do in the end. But in the first half of this semester, all 3 tests will be along the lines you've seen so far. The test with parts, with marks, you do it that way. From next semester, we've got 3 more tests to come in the exam. I'm going to start working towards writing reports so that you actually write, for me, something like introduction, if you like, of what the data is all about, what analysis is all about, your methodology, what kind of analysis will you do here, what your results are, what your conclusion is. And you can put all the R commands in the appendix somewhere, so I can follow the R commands here. But what I want in the report is basically explaining things more clearly in English. Yeah, so you're becoming more like a data analyst. This experience of report writing is something that will really serve you well. You probably don't get the chance to look at these kind of things mainly by the time you get to third year or so, and they start hitting you with this kind of stuff. I want to start it early, so you learn doing it now, and by the time you get to third year, you can do this properly, raise the level of things a little bit. Now, having said that, of course, when the first report is due for the first test after the break, you can expect the marking to be appropriate because this is your first report. In the second and third, the marking can increase in how much we look at things more carefully. By the time we get to the exam, then we can mark a little bit more harshly if that's required. But I think you'll be fine. We will be looking at report writing styles. There are many styles we can look at. I'll look at what I want from you in this kind of stuff. Many of the kinds of reports I'm looking for, if you like to look at, say, stats consulting reports that we produce here, the first part is going to be what we call an executive summary. We basically explain what the data is all about, what the interest was, what you did, what you found, done. You know how executives work. They haven't got time to read the whole thing because they aren't speed readers. All they do is read the abstract, the first part. If that makes sense to them, that's it. Somebody else can work the details out and explain them to him or her. So that's all they'll read. So everything that you've done there needs to be there in sort of a half a page to a page maximum. They haven't got time to read 10 pages. Half to 1 page maximum is everything you need there. Then the report will have all the details here, and we'll explain how that works and how you write the thing down, because writing is a skill that is going to serve you really well. There's 2 things, reading and writing, yeah, the 3 R's, reading and writing. Reading fast and writing well will really put you ahead. Now, going back to the speed reading for a second, if you can be in a job situation where your employer gives you, your boss gives you, your manager gives you, here's this document, please read this and come and explain this to me on Friday. And you got this on Monday, and you go to his door, knock, knock, good morning, can I talk to you? Yes. Here's the report, this is what I found. Now, most likely, your manager will give this to you and you and you and you, right? And those guys will be there on Friday. You've done this on Tuesday morning, bang, straight away. That will certainly start rising you above the rest, yeah? So you can be seen head and shoulders above your colleagues. And that's the kind of stuff that makes you go ahead in life, to be noticed. Not by blowing your own band or your own trumpet, but by doing things that make you noticed. That's the main thing, yeah? So that's my idea behind doing all this stuff. So come next half of the semester, we will be looking at some reports. Not only will I give you the format of the report, I should also give you an example report to look at as well. So you've got nothing, no excuses. Yeah, and I understand students complain all the time about things and how difficult they are. But you see, if you do all the work and look at things properly, you know, what students tend to do is they cherry pick things. They look here and here and here and here, and they miss the in-between stuff. And often the in-between stuff is where the details are, and whereas we know details are important, yeah? So somebody might look at the lab questions and look at question 2 and never look at question 1, whereas the information on how question 2 actually works is in question 1. And I get these 10 emails about this all, you know, at midnight or something, saying, how does this work? And I say, look at question 1, look at question 1, look at question 1. Now, if you do this about 20 times a day, you might get sick of it, yeah? I haven't got sick yet. Still okay. So make sure you do the whole thing properly, totally. It will really benefit you. Don't just cherry pick things. So again, repeating that you will get not just the report format, but also example reports to look at. It's worthwhile looking at them carefully. Writing is a real skill that helps you a lot in life. Yeah, it's not just what you've written; it's how you've written the thing as well, and how you can condense things and make still sense of it. It's the right kind of words you use. And essentially, one of my colleagues, in fact, my ex-PhD supervisor, who's now retired, his point was, as important as it is to make sure you're understood, is that you're not misunderstood. Yeah, understood as not misunderstood. So write carefully, and students write things and never read it back to themselves. You write stuff and you read the thing yourself. Yeah, read the thing yourself, because self-critique is the important thing that you will need to learn for yourself. You critique your own work and improve the thing before you give it to somebody else, so they can read the thing and say, this is perfect. No problems with this at all. Yeah. Any questions, my friends? Had a good hour and a half. This is meant to be 2 sessions, but it's essentially 45 minutes each, so I want to go over time. All good so far? Fantastic. See you next week, unless you come to the memory club on Wednesday afternoon.